Probability and Statistics, Chapter 9, Section 9.3. Tests about a population mean. 9.2 is tests about a population proportion. So we're going to add to that, how do you do a population mean testing? State and check random 10% in normal large sample conditions. Sounds familiar to the population proportions. Performs significance test. Use confidence interval to draw a conclusion for a two-sided test. Perform significant test about a mean difference using paired data. So, confidence intervals, significant tests for a population proportion are based on z-values from the standard normal probability distribution. Inference about a population mean, mu, uses what is called a t-distribution. Some call it a t-student distribution, with n-1 degrees of freedom. What does that n-1 degrees of freedom mean? Sort of like when you're picking sides for a kickball game or something. You have a bunch of choices until you get down to the last person when you don't have a choice. So if you have 10 people and you choose 9 of them, you've got choices. But when you get to that 10th person, you have to choose that last person. So this is like that's what I think of when I think of this degrees of freedom, n-1. We learned how to construct confidence intervals for a population mean in section 8.3. That's the population mean. 8.2 was the population proportion for confidence intervals. We'll now do testing a claim about an unknown parameter. In the early example, a company claimed to have developed a new AAA battery. Lasts longer than its regular AAA batteries. Based on years of experience, the company knows that regular AAA batteries last for 30 hours of continuous use on average. Simple random sample, 15 new batteries tested, and they lasted an average of 33.9 hours. So 3.9 hours better. Okay, then it must be better. Standard deviation 9.8. But is this convincing evidence? Just because it got better during this 15 batteries doesn't mean they're all going to be better. But is this maybe convincing evidence that new batteries last longer? To find out, we do the same type of significance test we did for proportions. Now it's the null hypothesis. Use mu instead of p. Mu is the population mean. The null hypothesis always equals. And they're saying, so what they found over the years, they last for 30 hours. That is the population. We're saying that this is now greater than 30 because it lasted longer. Of course, mu is the true mean lifetime of new deluxe AAA batteries. We introduced the conditions, random 10% when sampling without replacement, and the normal/large sample. These three conditions must be verified also for this significance test. Normally, there's a statement in the problem that says that this is a well-designed random sample. When sampling without replacement, this 10% rule, 10 times the sample has got to be less than the population, or the sample's got to be less than, at worst equal to, 1/10 of that population, capital N. The normal and large sample for a normal distribution is that n greater than or equal to 30, if you remember that. If the population distribution has a unknown shape, then you've got to have that 30 or better. If n is less than 30, then you've got to use some sample data to figure out if it's close to normal. Do not use t procedures if the graph shows strong skewness or outliers. So how do you carry out the significance test? Do the calculations assuming the null hypothesis is true. Test statistic measures how far the sample diverges from the parameter in standardized units. So just like we did before, this is the same wording really. Test statistic is statistic minus parameter over standard deviation of the statistic. Remember, for the proportion, it was p cap minus p over the square root of n of pq over n. Well, in our case, the mu sub 0 and the mu are going to be the same. The standard deviation is divided by that square root of n stuff, the central limit theorem. So, it will be the statistic x bar minus the parameter mu sub 0 over the standard deviation of the statistic, which is that s sub x over the square root of n. This is really the standard error instead of the standard deviation. When normal conditions met, then we can use the t-distribution with n minus 1 degrees of freedom. So, battery company wants to test null hypothesis mu equals 30 versus alternative mu greater than 30 based on a simple random sample. That's the first thing. 15 new AAA batteries, that's our N15. Lifetime standard deviation x bar 33.9, s sub x 9.8. So the test statistic 33.9 minus 30 over 9.8 divided by the square root of 15, 1.54. So you get that normal distribution. It works because, oh, hold it, this is 15. This is, how do we know we can use that? I think we know that these are normally distributed in the sample distribution that we grabbed from before. So we don't have to worry about that being 30 or better. So this is the p-value. Find that t-spot, 1.54. Find the area under the curve to the right of 1.54 using the t-distribution. And what do you get? Well, there's another table in there for the upper tail probability. Degrees of freedom. Since we've got 15, we count down by 114. Try to find 1.54 in the middle here. So we know it's between this 0.1 and 0.05. So the upper tail probability p is between 0.1 and 0.05. The p-value then is between 0.05 and 0.1. That area. We can find out exactly what that is by using our t-distribution on the calculator also. Table B gives possible range of values. We can still draw a conclusion if we had a single probability by comparing the p-values. It includes probabilities for t-distributions with degrees of freedom 1 through 30 and then skips to 40, 50, 60 up to 100 and 1,000. The bottom row is really for infinity, which corresponds to the standard normal curve. Use the lower degrees of freedom whenever you don't have the exact one. So anything between 30 and 40, use 30. Between 40 and 50, use 40. It shows only for positive values, but you can find it for negative because it's symmetric about 0. So when conditions are met, one sample t-test, the t-statistic, x bar minus mu sub 0 over the s sub x divided by the square root of n. This is the one-tailed, right-tailed, left-tailed, two-tailed tests. We need an example. Let's see. Well, first of all, the two-tailed test is exactly the same as the confidence interval, just as it was in the proportions. Both inference methods for means use the standard error of the sample mean in the calculations. So, two-sided test of significance, alpha at 0.05, and then it'd be a 95% confidence interval, gives similar information about that population parameter. Two-sided significance test at level at level alpha rejects the null hypothesis. The confidence interval will not contain the hypothesis value. So if you reject the null hypothesis, your value won't be in that confidence interval. When it fails to reject the null hypothesis, then the confidence interval will contain that mu sub 0. So, what about paired data, before and after? It's many times a comparative study. Those are usually more convincing than single-valued. One sample inference is less common than the comparative one. Two observations, the same individual, one before, one after, things like that, use paired data. So we're not then using this the value twice. We don't have to use that. We can just take the differences in each pair. If the conditions for inference are met, we can use the one sample t procedure on the mean difference, mu sub d. These methods are sometimes called paired t procedures. So here's an example. Researchers designed an experiment to study effects of caffeine withdrawal. They recruited 11 volunteers diagnosed with being caffeine dependent to serve as subjects. Each subject was barred from coffee, colas, other substances with caffeine for the duration of the experiment. During one 2-day period, subjects took capsules containing their normal caffeine intake. During another 2-day period, they took placebos. The order in which the subjects took the caffeine and placebo was randomized. That's what, so we would get rid of some of that problems that you might get. At the end of each 2-day period, a test for depression was given to all 11 subjects. And they wanted to know if being deprived of caffeine would lead to an increase in depression. So the table contains the data for the 11 people. Depression, caffeine, depression, placebo, difference. So I guess they did the placebo minus the caffeine. So that's why here 0 minus 1 gives you a -1. The only negative in that list. Problem. Why did researchers randomly assign the order? They wanted to be able to conclude any statistically significant change was due to the treatments, not to some other variable. One other concern, suppose the caffeine were given to all subjects during the 2-day. What if the weather were nicer on these 2 days? Things like that. You don't want to have anything influence the scores due to something outside, like the weather. Random assignment of the two, caffeine and placebo, should help ensure no other variable, like the weather, is affecting. So carry out the investigation. If the caffeine deprivation has no effect, they would expect the actual mean difference to be 0. So we're going to ask the question, if there is no effect, the mu sub d, the difference, would be 0. The alternative greater than 0. Now you could say not equal to, perhaps. But the depressant, we're trying to look at things going greater than, not less than. I guess. Music D is